All right. So great. So we'll start with F equals MA. We'll start with the first question. So this is about some sort of like dumbbell in orbit around a planet. And we're asked essentially about equilibrium and stability of equilibrium of this rotating object. So I sort of didn't put the answer choices just because basically answer choices are just all the possible options. So we'll just do it directly. All right. So you have a planet, and then you have some orbit around it. And then around the orbit, you have so on the orbit you have this sort of two masses which are equally spaced. The distance between them compared to the radius is not negligible. So it's not just like a really small distance, it's a non-trivial distance. And this object is rotating in such a way that it always remains vertical. So it's always rotating such that, here, my bad, it'll also remain vertical and so on. So the question is, if it's doing this process, what does that mean about the tension or compression in the rod? Okay, so this part is not so bad. Let's just work it out. So the idea is to set it off free body diagram, consider the forces on the masses. Well, actually, maybe I'll give everybody just 1 or 2 minutes to think about it. Yeah, this is a good question to think about on your own for a bit. So yeah, just think about it for 1 minute and then we'll talk about it. So just determine whether there's tension in the rod or compression in the rod, and then if you have time, think about the stability of the equilibrium as described in the problem. All right, so let's do the question. So let's say for now that there's a tension T in the rod. If T turns out to be negative, then we'll know that it's compression. So what that means is that on this guy there's a tension force T upward, and there's a tension force T lower on this guy. And let's let the radius to this orbit be r, and maybe let's let this distance be L. So the length of the rod is 2L. Then what we get for the top mass, excuse me, is that and suppose let's say it's rotating with angular velocity omega. Then for the top mass we get that GMM plus T this is just F equals ma. This is the total net force. The thing on the first thing is the total net force on the object. The second thing is the centripetal acceleration. And similarly, we get minus T equals m omega squared r minus L. Right. So from here, the question is whether t is positive or t is negative. All right. So have I done something wrong here? No. Okay. So you can sort of do this in two ways. One way is you could sort of solve for t and try to analyze, but then a simpler way is the following. What you can say is that you can sort of take L over, even though the problem says we can't do it, we can sort of assume L over R is much less than 1 just to determine the sign of t. And then we can sort of think about it like that. Actually, why am I doing this? Let's just solve for t and then we'll analyze the signs directly. So the idea is that omega is the variable which is not we don't know anything about, so we have to eliminate that. So if we eliminate that, we can multiply the first equation by R minus L, the second one by R plus L, and see what we get, and then subtract them. So we get so t is equal to 1 over 2r times gmm. So now the question is whether this quantity is positive or negative. So again, positive would mean tension, negative would mean compression. So if you think about it, you can realize that this quantity is positive, because if you cross multiply, then what you get is you get R plus L cubed minus R minus L cubed on the top over a common denominator. And this is positive. So T is positive, which means that we have a tension. So that answers the first part of the question. Any questions about this? Somebody asked, why will tension have a force in that direction? I assume you mean like up here. That's just how tension works. So in tension, if you ever have a rod or a string in this direction, then the tension force on this mass will always be pointing in this direction. It's just how tension works. It could be pointing in the exact opposite direction, but that's just analogous to T negative. That's why we said there's also a possibility of compression. No, so somebody's asking there's compression, right? No, we found that T is positive. And the way I set the problem up is that T is pointing inward for the lower mass and T is pointing outward for the upper mass. That's what you get when you do tension. Okay, so so I'm getting many questions, which is good. So to answer the first question, there's not compression. So I understand why I might be being confused, but think about back to regular like pulleys in physics. If you have like a pulley with masses here, the tension is always pointing into like the string, like on the mass, sort of in the direction of the string, and that's a tension force. So if you think about the string as being stretched, then that's pulling the masses on the ends closer together. That's sort of the force that's being applied. That's why the force directions that I've drawn here correspond to tension, not compression. Next question is, the question reads, could you say that the gravitational force on the mass that's farther away from the planet will be less than the one that's closer? So there will be tension that results to keep them together. No, you cannot say that. The reason is that they're at different radii. And since they're orbiting with the same angular velocity, but they're at different radii, that means that their sort of centripetal acceleration that they need could be different. So you have to argue using these equations because these are the actual equations. In particular, these terms are different for both of them. So that means that you have to argue like this. Alternatively, what you can do is you can go into the rotating frame, and in the rotating frame you get an extra centrifugal force pointing outward, and you have to account for that. It's equivalent to accounting for centripetal acceleration here. So you can't just account for gravity. It gives you the right answer in this case, but it's not a correct solution. Okay. Hopefully I've answered the questions. Can you please tell what is actually meant by compression? So I would suggest if you're getting confused about tension and compression, which is certainly a valid thing to be confused about, just look it up. Look up tension versus compression, and I'm sure you'll get many resources that'll help you. But just in short, tension is so okay, so yeah, so that's the answer to that question. Somebody is saying you can use v squared over r plus L instead of omega squared r plus L. You cannot, because you could, but then the point is that the v's for the different masses will be different. So like the idea is that, so the person is asking whether instead of using omega squared r, we can use v squared over r. That's not really correct, because these two masses are going to have different velocities because they're orbiting with the same angular velocity about this planet, because they have to like be in phase. So they'll have different speeds. So you could calculate that, but it's just more calculation. This is the more direct way to do it. Okay. Any more questions about this part? Okay. Appears to be no more questions about this part. So we'll move on to the equilibrium part. Now, one thing to note is that the equilibrium part is significantly trickier to think about than this part. But on the actual test, this were sort of, if you will see the test options, this would reduce you down to two options. One is that tension stable and tension unstable. Those are the two options. Depending on how confident you are in your abilities, you could either try to think about it, but for many people, the right strategy once you get to that point would just be to guess and move on, because that's just one binary thing left to determine, and like it might not be worth it if you have a lot of questions left. That's just a test taking strategy. In this problem, you would be able to, if you did this, you would be able to reduce down to two options. Okay, but let's do the reasoning here. Okay, so let me redraw the picture. Okay. So what this problem is saying is now you sort of have a you perturb the rod by a little bit in the theta direction. So you perturb the rod to like now like that. And the question is, when you perturb it like this, is it stable or unstable perturbation? And the way you set this up is that you set it up such that within in the rotating frame, in the omega rotating frame, it remains stationary. So basically what this problem is telling us is we should work in the rotating frame and analyze the problem there. So in that rotating frame, what's going to happen is that again, there will be this gravity force, and then there'll be the tension. So there'll be tension and gravity, but for each mass, so maybe I'll draw a bigger picture here. So gravity, tension, and now there'll also be centrifugal force. This is work in the rotating frame. Okay. So the question now essentially is now when you rotate this thing by a bit, if you rotate this by a bit, then is the equilibrium stable or unstable? And you rotate it by a small angle. So the thing to realize here is the following. We essentially have a very fast oscillation. So tension, which being an internal property of the rod, will not be able to change very fast. In particular, we can sort of assume the tension will remain constant throughout this oscillation, constant to what it was originally when you perturb it a bit. So that's one thing you can assume, but the gravity and the centrifugal, which are sort of like properties of how far it is from the center of this planet, are going to change potentially. So we can assume that the tension is constant when we rotate. It's the same because it's a physical internal thing of the rod, which doesn't have that much. The time scale for which for that to change is too long for this process. But potentially gravity and centrifugal change. However, the thing to realize is that the distance to the, if this distance is L, the amount that the distance to center changes by L times 1 minus cos theta, which is actually on the order of L theta. It's on the order of theta squared. So the amount of the distance to the center changes are on order theta squared. That's fine. But what that means is that up to order theta, the forces don't change. And now we already saw that the gravity plus centrifugal should cancel out tension if the thing is vertical. So what that means essentially here is that what you can think about is that in your rotated case, you have tension. And then the net sum of gravity and centrifugal should be sort of an equivalent tension force pointing down. This is not, maybe I'll call it F net from gravity and centrifugal. And F net magnitude equals T. Because this F net, what we're saying is that it's only changing by order theta, so we can assume it's also the same as what it was when it's vertical. And what this means now is that the torque on this guy is F net times L. There's also one here. Sine theta times 2. And again, I mean centrifugal because we are working in the rotating frame. So if you don't know fictitious forces, I don't have time to explain right now. I would suggest you look up fictitious forces in Morin or something and read about that. But this problem really requires knowledge of fictitious forces to solve the second part. Okay. So this is the torque on the dumbbell. And again, you can see here that this is order theta. So if we were to include any order theta squared correction to this term, it would not affect the product. Somebody said basically Newton's opposite force for centripetal. That's wrong. I'll go over that after finishing this problem. Okay. So and then this is positive. If you think about the forces here, this torque, it's restoring the angle. It's making the angle smaller in this configuration. So the torque is restoring, which means that the equilibrium is stable. So there were a lot of things that went into the reasoning here. Basically arguing, first of all, working in the co-rotating frame, then saying that tension is approximately constant, then arguing that the distance to the center doesn't change that much, just only changes by order of theta squared, so we can take it to be basically constant as well, and then doing the geometry argument to show that the torque is restoring. Those were sort of the steps. And again, it's possible to just mess up one of these steps and get the wrong binary answer and convince yourself, just stable or unstable, and that could cost you the entire question, and a lot of time. So depending on your level, it might be better once if you do the first part to simply just guess the other two options, or one of the other two options, and just move on. That sort of maximizes your expected value of your score, without wasting too much time. Okay. I guess somebody mentioned Newton's opposite for centripetal. I should just clarify that that's not really correct. Newton's opposite force is something completely different. What Newton's opposite force says is that if two objects are applying a force on each other, and the forces they apply on each other are positive and negative, are opposite and equal. So like what Newton's third law says is that if I let's say have a wall and I push on it, or let's say there's a book and I push on the book, then the book applies a force on the wall, force from book on wall, and then the wall provides this exact opposite force to the book. Centripetal versus centrifugal has nothing to do with this. The correct analogy for centrifugal is the following. So sort of the most simple, I guess I'll just talk about fictitious forces for a couple of minutes. The simplest case of fictitious forces is just a linear acceleration. So what you can do is you can imagine that there's a car, or let's just say it's a box, and that it's, let's say in the inertial frame, so in the frame of the ground, it's accelerating to the right with acceleration a. Okay, now let's think about what that means for a little mass inside. So let's say this mass has like a force F on it or something. And then let's say the position of this mass, and let's just say everything is in one dimension. So maybe that force is, let's not work in two dimensions. That force is in some one-dimensional force. And the position of this is X in my lab frame. Then what F equals ma will say is just simply that F equals mx double dot. Because it doesn't care that it's in a box just accelerating. But now let's look at it in the frame of the box, which is accelerating. In the frame of the box, sort of the coordinate of the particle now relative to the box, the coordinate of the box is now x sort of, we can take it to be x minus at squared over 2, because the sort of the back of the box moves by at squared over 2. So this is the new coordinate. We can maybe call this coordinate x prime. This is the coordinate in the frame of the box. Then the second derivative of x prime is now is this, which means that the F equals ma equation will now read F equals I think I've messed something up here. Sorry, just give me a sec. Yeah. So what this then means is that a is the constant acceleration of the box, which means that F plus negative ma is equal to mx prime double dot. And in the frame of the box, x prime is sort of the true coordinate. So what we're saying is that in the frame of the box, it looks like there's a negative ma force everywhere in the frame of box. So in the frame of the box, it looks like there's a negative force ma pointing backwards. This is like when you're in a car, you feel pushed backwards. That's what this phenomenon is. So we're just shifting the frame, so you're dealing with centripetal force, you're dealing with centrifugal force. I mean, that's a way to think about it, but the idea is when you shift frame, then you pick up this sort of fictitious force. It's called fictitious force because it's not real. Newton's third law of forces are real. Fictitious forces are just like a mathematical convenience. Basically, in accelerating frames of reference, Newton's laws don't really hold anymore. But you can sort of use fictitious forces to sort of cheat and modify them by saying, if you add this extra centrifugal force everywhere, then Newton's laws do work. And that's what we're doing here. And the reason it's useful is because it's often easier to think about. It's easier to think about the problems in the rotating frames, but then you have to add this extra fake force, which is a centrifugal force, to make Newton's law work, because it shouldn't work normally because it's an accelerating frame. Anyways, but I would suggest that you read like the Morin Blue Book chapter 10 has a good exposition on fictitious forces. So if you're confused about them, you should read that. Okay, but besides that, are there any questions about the stability question? Could you go over again what the point of the L times 1 minus cos theta argument was? Sure. What this is saying is the following. When I rotate the dumbbell, potentially like let's do it here. When I rotate it, let's say I rotate it by a lot. Now the distance to the center has changed. The distance of the masses to the center has changed. So the gravity force is different. The centrifugal force is different. So in my calculation, I have to now do different values for the forces. I can't just say that F net, basically saying F net equal to T down here was the equivalent of saying that these forces don't really change when you rotate a bit. But what I'm saying now, the L times 1 minus cos theta, is that's the order by which the distance is changing. And it's changing by essentially order theta squared. So yes, rotating by a small angle theta will change the distances to the center, but it changes it only by order theta squared. So it's not relevant on an order theta calculation. Does that make sense? It's just to calculate the change in distance and prove that it's on order theta squared so that we can ignore it when I'm doing an order theta analysis. Yeah. And basically when you're dealing with oscillations in the force setting, you want the force to be, the torque or whatever, to be negative, to be proportional to the angle. So proportional. So like in reverse, you want the restoring force to be proportional to the position coordinate, which in this case is angle. So we don't only care about up to order theta, not order theta squared. Okay. Maybe I'll just wait 15 seconds for another question, and then we'll move on to the next problem if we don't get any more questions. Okay, let's move on. So you can go to the end of the PDF, the second last page of the PDF, to get the problem. And again, I would suggest everybody think about it for 1 or 2 minutes. It's a very F equals MA style question that's very important to know how to solve. So yeah, just take a minute or two to think about it. Somebody's asking whether the ball roll means it's also rotating on the plane. Well, this is just saying the ball is rolling down the plane. Like, I'll leave it to you to whether that implies rotation or not. ball rolling down the plane is a standard enough concept that it shouldn't require further clarification on a f equals ma problem. Oh, I guess it hasn't said whether that the ball is rolling down. So yeah, but yeah, just think about the question for a bit. I don't think the question needs clarification at this point. Okay, just 30 more seconds and we'll get started. All right. So yeah, let's start. So important setup: the static and kinetic friction have equal value. This is a bit unrealistic assumption, but it'll be important for our analysis. But just remember that. Okay, but what the problem is saying is you have inclines and you change the angle theta, but you always set them up such that they have the same height. And then you take a ball and you just let it go down. Naturally it will roll sometimes and it'll slip sometimes and get down. So the point is, for small enough angles theta, it'll roll without slipping. And when it's rolling without slipping, no energy is lost. And all the energy goes into kinetic energy, translational plus rotational. The reason for that is when it's rolling without slipping, it means that the force of friction is always static friction. And whenever it's rolling without slipping, the point of contact is stationary, is instantaneously stationary. So there's no slipping, and there's always static friction, and there's no energy lost. So, and then it rolls without slipping up to a critical angle theta. And so for 0 less than theta, less than critical angle, no energy is lost. So it must in fact be the graph must start off at a constant for up till some critical value of theta. So that reduces to C, D, or E. So we have C, D, or E left. Let's eliminate D first. So what the idea for D is that this is where the coefficient of static and kinetic friction equal come in. What this is saying is for theta a little bit above the critical angle, since the static and kinetic friction are equal, there should not be a discontinuity in what we get. And what D is saying is that there's a massive discontinuity in the amount of energy lost. And that should not be the case, since the static and kinetic friction are equal. So there's no way to get a discontinuity. Normally, get discontinuity is because when you change from not slipping to slipping, the coefficient of friction changes, so you get a discrete discontinuity. Here, that's not the case, so you should not expect a discontinuity. So it can't be D. And to eliminate E, we think about theta equals 90 degrees. When theta equals 90 degrees, there's absolutely no normal force with the incline and therefore no friction force with the incline. So it'll just fall down with no friction force and all the energy will be turned in. So at theta equals 90, it should also be at the max, at the full energy. MGH energy should be going into kinetic energy. So that means that it must be C, because the final value at theta equals 90 should be the original value for theta small. So that's how you solve the question, but I think there's a lot of details here which are skipped. So depending if people want me to go into more details, we can go into more details and sort of derive the critical angles and think about various things like that. If not, we can move on to the next question. So it depends on what everybody wants. So if nobody says anything for the next, okay, cool. So I'll answer that question. Yeah. Okay. So let's talk about rolling without slipping. Let me erase this. All right. Okay. So what are the forces on this object? There's gravity. There's friction. And there's normal force. Let me just draw that again. Okay. So those are the three forces on the object. And let's say it's accelerating down with acceleration A. And let's say it's clearly going to be rotating downwards, but it might not be rolling without slipping. So it's rotating down with angular acceleration A. Okay. Just give me one sec. All right. So let's write down the F equals ma equations. So what we get is that mg sine theta minus F equals ma. That's just the that's the x sort of, if I call this x, that's the x equation. The y equation is that n minus mg sine theta, sorry, mg and finally the torque equation says that F is equal to this is the torque and this is the moment of inertia times the angular acceleration. All right. Great. So what this means now is the following. So basically there's two options. Option one and option two is rolling with slipping. So the way to determine, so sort of there's a fundamental principle in friction, which is very important here. The fundamental principle in friction is that you should always assume that the friction is static. And in static friction, the friction can take any value. It can take any value less than or equal to the normal force times the coefficient of static friction. So you should always assume that the friction is static. And you should solve for the friction. But if you get the friction value is less than or equal to normal force times the coefficient of static friction, then it actually is static friction. But if you get that the value is bigger, then that means that it was actually what the force was too large and it must have been slipping. So you have to then redo the calculation with the coefficient of kinetic friction for slipping. And the idea is that fundamentally friction is static, because if you think about like just a block on a table and you pull it with a force, it's going to be static until it finally starts slipping. So again, the point is that it's always going to start off as static friction, and then once the frictional force is too large, it's going to then start slipping. So again, what we should assume here is that we should assume that the force is static friction for small values. And then we should solve and see if the force is less than or equal to normal force times coefficient of kinetic friction. And if it's not, then we're in the slipping regime. Does that make sense? Does that logic make sense, I guess? Maybe here's an alternative way to justify it. Let's assume that slipping was happening. Let's assume slipping was happening, and then we'll show that that's not possible for small values of theta. So let's go to the equation. So slipping means that F is actually equal to n mu, because in slipping we always have F equals n mu. So what that means is that mg sine theta minus n mu equals ma. N minus mg cos theta is 0. And fr equals I alpha. So what these imply, so F here, I should say, what the first two imply is that mg sine theta minus mg mu cos theta is equal to ma. So A is g times sine theta minus mu cos theta. And the point now is that if theta is small, then this quantity is negative. You can think about the function. So which means this is a contradiction. So we cannot be in the slipping regime for small theta, because if we are in the slipping regime, we get a negative acceleration, which makes no sense. So in fact, for small theta, we must be in a non-slipping regime, which means it must be rolling without slipping. And in this case, then we have that alpha is equal to a over r, which then we can solve the equations using that. And again, now this also tells us the critical value. The critical value is this is the smallest value for which it starts slipping by this equation. Okay, somebody asked a question, Boris, in the chat. Why OX F less than 0? I don't understand that question. Can you just clarify the question? We've never said F is less than 0, so I'm not really sure what you mean. We've said F is less than or equal to n mu times S. This is the condition for static friction. Static friction. But what exactly are you asking? On the x-axis. Yeah, so what's f, why is f, who said f is less than 0 on the x-axis? Oh, that's what you mean. All right, okay, I understand. Why is f pointing backwards on the x-axis? Okay, sure, that's a good question. The reason for that is think about what's happening in the process. Yeah. What's happening is that the object is moving down the plane. So if it's slipping, say, and its object is moving down and it's rolling, you can think that the contact point is moving forward with respect to the plane, which means the frictional force has to oppose that and be backward. Does that make sense? We can yeah, basically frictional force has to, so the sort of the reason I'm hesitant is the correct way to see this is to do the static friction case. So So to answer your question, the correct way is to solve the rolling without slipping case, static friction case. And in that case, f can take any value, and you'll actually be able to solve for the exact value of f. And when you do that, you'll find that f is pointing in the negative x direction when you solve in the static friction case, when it's rolling without slipping. Then in the sort of boundary between then it starts slipping, by continuity, it must remain pointing in the same direction. So since in the rolling without slipping case, it's pointing up the plane, it'll continue pointing up the plane once you start rolling with slipping. Because in fact, the frictional force can be pointing in the direction of the motion. So it's not true that the frictional force always points backwards to the motion. In particular, if you like have a car and the car is has tires, and the car and the wheels start accelerating, and then this accelerates the car forward, the actual force that's the sort of Newton's law's force that's pushing the car forward is a frictional force pointing forward on the tires, because there's no other interaction between the car and the universe. So my point is that frictional force is not always pointing backwards. You can't just say it's pointing backwards to the motion. What you have to do is you have to solve the rolling without slipping case. You'll find that frictional force is pointing backwards, and then therefore it'll be pointing backwards for all cases by continuity. Does that answer your question? But perhaps that's too complicated of an explanation. The idea is in simple rolling without slipping cases, friction always points up the plane. But sort of the static friction continuity argument was the more detailed reason as to why this is the case. All right. Cool. So right, so that anyways, but the sort of the main question was about this graph, and I think any questions about the graph or anything I said afterwards about the original problem or anything I said afterwards. And then if not, we'll move on to the next problem. Yeah, so people are asking why the graph has to be continuous. That's a very good question. The short answer to why the graph has to be continuous is that the static friction and the kinetic friction coefficients are equal. So we shouldn't expect there to be a discontinuous change. I mean, the more detailed reasons you have to go into the equations. And when you do that, basically it's the same exact reason in the equations. Is these are the fundamental. So let me just talk about this in a little bit more detail. These are the fundamental equations. These hold true in slipping, non-slipping equally. But in the rolling without slipping case, what ends up happening is that you can relate alpha and A in the rolling without slipping case. And in the rolling with slipping case, well, you can't relate those two because there's no more rolling without slipping, but you can then instead you can relate F and N. So always you have the same number of variables equation. So you're always able to solve this depending on which regime you're in. But the point is now for angles around the critical value, if you look at both regimes, the equations the equations have very similar values before the regime and like inside the rolling without slipping and outside the rolling without slipping, because the equations are essentially staying the same. And the sort of the change happens when the frictional force the static friction force exactly reaches the value of n mu. So if you look at theta slightly larger, the equations essentially stay the same, and none of the variables are changing discontinuously. Basically, you're solving a system of equations, and none of them are changing discontinuously. The potential for discontinuity would be in that when you're solving now the static friction, the kinetic friction case, i.e. the slipping case, the F equals n mu is different than the F less than equal to n mu that you had for static friction. So that boundary is different and it discontinuously shifts. Otherwise, when you go into the slipping regime, just a very tiny bit into the slipping regime, there's no reason it should drop by a large amount, because if you go a very tiny bit into the slipping regime, what you'll see is that the gravity force is basically exactly the same. You just increase the theta by a very small amount. The friction right before the slipping regime was n mu, because that was the critical value of the friction, and in the kinetic case, it's still equal to n mu. So it didn't change at all, but also the change for F is very small. The normal force is still mg cos theta, very small, basically the same as before. And again, we argued F is the same. So basically, all the parameters are the same. The reason this would change, and it's continuous when you solve for A and solve for all these things, it's continuous. The reason this would change if the kinetic and static were different is that the boundary between the two regimes is when in this rolling without slipping case, when F is equal to n mu s. And right when you start going into the slipping case, then you set F equals n mu k. So now right before slipping, slipping and right after slipping, the value of F changed discontinuously. But in this case, since the coefficients of friction are equal, none of the variables change discontinuously. So when you solve for A, you should not expect it to change discontinuously as well. That's a sort of long answer to just saying that the coefficients of friction are the same, so it doesn't change. All right. Any other questions? Can I scroll down to the slipping? Sure. This is the slipping calculation. Okay. Great. So I assume I'm not getting any more questions, so we'll move on to the next problem. And that's again also on the last page. Excuse me. So 2018A, problem 17, I mean. So this is actually a very deceptively tricky problem. I got this problem wrong when I did that field I made back in 2018. But I'll give everybody a minute to think about it, and then we'll go over the solution. So yeah, just think about it for a minute, and then we'll talk about it. All right. So let's think about this problem. So In order to simplify our analysis in the beginning, let's forget about the turning back, and let's just see what happens for when you move just with constant velocity and you drop sand out. What does that look like to somebody standing on the ground? And then we'll sort of slice those together to get the answer for 17. But let's just analyze that first. So you have your helicopter thing. It's moving with velocity v. And let's say at time t equals 0, it drops a little particle of sand. The key is that this particle of sand is going to have a velocity v in the same direction too. Because when it drops off, it's dropping off at rest with respect to a helicopter, which is already moving with speed v. So therefore, it has a horizontal velocity v when it starts with respect to the ground frame. And then it accelerates down. And then it accelerates downward. But the point is that now the position of the sand in x direction equals vt always, because there's no acceleration in that direction. This is kinematics. It's always vt. And similarly for the helicopter. So actually, this particle of sand is always below the helicopter. So what this implies is, barring change of direction, the particle of sand is always below the helicopter. So every particle of sand, assuming no change of direction, at all times is right below the helicopter. So that actually means that at any point in time, the thing you must be viewing is just a stream of particle of sand, all right below the helicopter. And the reason is that we just proved that any particle of sand will always stay with the helicopter in the x direction. So that actually implies D. We don't even have to think about the change of direction anymore. And you can think about it and you'll get part D, but the point is that the graph of the sand has to be just a straight line down from the helicopter. Any questions about this? I know, I think when I present it like this, or when you read the solution, it might seem very simple. But it's sort of very subtle, the fact that the sand always stays below the helicopter, so it looks like a vertical line. I don't know. Maybe it's obvious to other people. I don't know. For me, it was just that year on that day, there was like, this is one of the questions I got wrong for some reason. I think I put one of A or B. But yeah. Why is there discontinuity? What happened there? So yeah, this is a good question. So this is actually not a true discontinuity. The reason being that somebody asked, why does the answer D have a discontinuity in it? The reason is that, think about what this means. Like, what does that discontinuity mean? It means like, so let's just think about the process. Let's just analyze the process in more detail, and then we'll just see the discontinuity up here. So once the helicopter started here, and let's say it gets all the way to its final point on the right, and at this point has a bunch of sand below it. Now, as it moves a little bit to the left, there's sand below it, but this chunk of sand is still going to be falling down with V. And the point is, once this reaches all the way over here, it's new. Let's say it's like new. Let's say this is its final state. It'll have a bunch of sand below it. But in that amount of time, this original sand right here would have already fallen by a speed v. Does that make sense? So that means that this will now be shifted down by v. The key point is sort of the discontinuity comes from this bottommost particle of sand here and this topmost particle of sand here. Also, by the way, I lied a bit. This is still also moving to the right. It's still moving to the right after the helicopter starts moving to the left. So this lower one is turned around by this. So this is moving. This is still a vertical line, And the point is, we're sort of interested in the discontinuity between this particle of sand and this particle of sand. Both these particles of sand are dropped at about the same time, all the way on the right, but they're dropped with one with velocity this way and one with velocity this way. So I'm pointing, you can look at me, hopefully you can see me as well. One is the particle of sand is moving to the right, which is the this one right here, and this one is moving to the left, because this one was right before the helicopter turned and this was right after the helicopter turned. So therefore they start at the same location, but then they moved like this. So that's why after a certain time, the snapshot shows them at a discontinuous distance apart. Somebody asked, to the time it takes to turn and get to a point and back, there's no sand falling down. I think what you're asking is that the point is that you can assume that the turning, that the change of velocity direction happens very fast. So you can ignore whatever sand falls in that period of turning around. Is that your question? That we can basically ignore the period of time in that turning around. Yeah, that's basically the problem. Says the helicopter suddenly turns. And of course, we shouldn't expect that turning, if there's a little bit of sand falls out, it shouldn't affect the answer in a very major way, because this is physics. Like, so it should be something close enough to D, and clearly all the other choices are very far from D. So it's not reasonable to assume any of the other ones would be the actual correct answer if you accounted for that time. So yeah, so somebody asked, can you talk about what the graphs are trying to show? I'm kind of confused about the way to describe the dot represents a helicopter. This is sort of what confused me as well. So these are not really graphs. These are not representing graphs as you conventionally think about it, like position as a function of time is a parabola for falling down. That's not what this is saying at all. This is literally like a photographer. Let's say the sand is colored so you can see it, and the helicopter is moving in the sky, and the photographer has a really nice view, and the photographer literally takes a snapshot. What do they see? This is not really a graph in a conventional sense. Each point in the so-called graph represents a particle of sand that fell at some point off of the helicopter. And just now, this locations of these particles of sand show up in this picture, and that's what the graph is. So it's not a graph. It's not a graph that's telling us information like, oh, is X is a function of time, B is a function of time, even Y is a function of X. It's just like a snapshot in time. This is what the sand looks like right now. That's why this is a little bit trippy problem. Because it's really just a picture that a photographer took at a certain amount of time. And the dot representing a helicopter just means that they just didn't want to draw a little graphic of a helicopter, right? Because that's what the photographer would see, right? So yeah, again, literally, these pictures are just photographs, essentially. Assuming you can see the sand very clearly. Does that answer your question? But yeah, I agree that this is trippy to think about, and that's why I put it here. No, it's literally just one photograph. Many photographs overlaid is more like a conventional graph, like, a parabola of a ball. No, this is literally one picture. So in particular, what that means is that each point, each pixel in the picture of the sort of so-called graph represents a distinct particle of sand. So it's literally just one photograph. Conventional, like, ball throw track, it's a parabola. You take many photographs and you overlay them and you get a parabola. This is not that. This is just one picture. Okay.
It's like they had like an air show, and there's like, and they decided that they wanted to make a picture.
Yeah,
to
sure,
write
exactly.
like
Yeah, exactly.
That's what the person sees from the ground.
Exactly. That's exactly right. Yeah, it's literally what the person sees from the ground. It's not some sort of physics graph. That's why this is trippy, because it's not your conventional physics graph, like overlaying pictures and plotting it on a graph. There's no plotting. It's just what it looks like at a certain amount of time. And that's why A and B are wrong, because A and B somehow, if you reinterpret the problem as sort of like a more physics graph, like plot things as a function of time and so on and so forth, you can convince yourself that it's A or B. That's why this question is very easy to get wrong. So somebody asked, could you quickly go over how you found the x direction equation, aka dt? So the point is that when the sand falls out of the helicopter, if you're moving in a car and you I don't know, this is not a very good, like, this is not a very good example because you can't have personal experience of this. But my point is, if you're moving, actually this is sort of an example. Let's say you're like let's say you're moving very fast and you like throw a basketball up, then like really high, and let's say you move with constant velocity, then you'll actually be able to catch it back where you started. Not where you started, but where you currently are. So if you're let's say running a constant velocity, throw a basketball in the air, and then you'll catch it right when it comes to the ground at your current location. What that means is that when you're running and you threw the basketball up, you just threw it in the upward direction, but since you yourself were moving in the positive v direction, positive x direction, the basketball got a positive x velocity imparted to it as well. And from a person on the ground, the trajectory of the basketball looks like a parabola from when you threw it to when you catch it. To you, it just looks like it's going straight up and down. But from the person on the ground, it looks like a parabola because it got an extra v velocity from you. Okay, that answers the question. The person said that answers the question, so that's great. Any more questions about this? Okay, so we're a bit low on time, and we have a lot of questions. We have 4, 5, 6, and 7 left. So I'm going to just decide that we're going to move on to problem 5 because I think the idea in problem 5 is really neat. So yeah, I'm going to do that. And of course, there's the F equals MA solutions manual, which I sent a while back. Afterwards, you can use that to read solutions to other problems. Those solutions are relatively well written in that solutions manual. Okay, but let's do this F equals MA 2018 B problem. So this problem is not tricky in the sense that the previous ones were. This problem, if you know the method, it's actually a very standard problem, but it uses a very novel method, which is why I put it here, because the method is very nice. But once you know the method, it's not particularly hard. It's not a particularly hard or tricky problem, unlike the previous ones, where you had to sort of think very carefully about what was going on. But since it's a nice idea, I just want to demonstrate it here. That's why I put it on. So what this is saying is you have a hemispherical shell. So this is actually a hemisphere. It's 3D, but we'll just draw it as 2D. And you have a particle of mass m, and the hemispherical shell radius r, and it has mass density sigma. So what that means is that per unit area on this hemispherical shell, it's sigma times the little area is the amount of mass. What is the gravitational force of the shell on the particle? So essentially what we're asked to calculate is that each little parts of the shell will provide a gravitational force on the particle, and you add them all up, and what do you get? Okay. Now there are two ways to this question. One way is sort of a standard method where you sort of split this shell into rings. You calculate the force from each ring, and then you integrate over these rings. Sort of, you can set up if this is an angle theta. You integrate over those rings. And then you solve it like that. That's boring. It'll take some time, but it's sort of foolproof and guaranteed to work. But that's a bit boring. So I'll show a really neat method for this problem, which is what I want to demonstrate here. So, but that's a standard way where you just split into rings, integrate over rings, calculate the force, and you win. Okay, but here's a nice method. So there's a couple of steps here. So step 1 is use Newton's third law. And now it's by Newton's third law, it suffices to find the force on the shell due to the gravitational field of the particle. So instead of adding up gravitational forces from each of the parts of the shell, we'll just take the gravitational force of the particle and add it up along the surface of the hemisphere. Now, the very nice thing that happens here is that the gravitational force only depends on the distance to the particle. And that distance is always r, because it's a sphere. So if I actually let f be f sub g, or hold on, let's let sort of the so-called gravitational acceleration be g little m over r squared. So now any part of the shell will feel a force if a little part of the shell has area dA, or area small area delta A, then the force felt is so g is like this constant value. So now the question is what is the total force? So the way we can do this is the following. The nice idea. So this is step one. Step two is the main idea. So this is just to show the 3D nature of the thing. Now consider a little patch of area here, delta A. Say it's at some angle theta. So it feels a force outward of sigma delta A times g, as we saw. But the point is that now these directions are varying depending on where your patch is, depending on the value of theta. The directions are varying of what this overall force is. But we know by symmetry the final force has to be pointing upward. So we'll only consider the upward component of this force. And that essentially amounts to doing sigma delta A times g cos theta. Now it looks like I'm doing the integration approach where you just add all these up and do the integral. But instead there's a very neat trick here. What you can do is you can rearrange this as sigma g times delta A cos theta. So instead of putting the cos theta on the force, we move the cos theta into the area. And geometrically, what is delta A cos theta? Can anybody tell me? So if you have a little patch of area on the surface of the sphere, is there a nice interpretation you can tell me of delta A times cos theta? Anybody in the chat? So you have a surface of the sphere, a little patch on the surface of the sphere with area delta A. What's it? Okay, so Evan has given a good answer. Projection onto the base of the hemisphere, exactly right. So delta A cos theta is exactly the area if you project that little patch. So the patch is angled at some angle theta, which is the same angle here, and it's the area of projection onto the bottom. This is actually the area of projected patch. So the sort of the net force, if you just take the z direction, which is by symmetry, will be the final answer. It's just sigma g times delta A projected. And now if you add this up over all patches, because the patches all project down to the base, this just becomes sigma g times pi r squared. And this is the final answer. You can take the value of g and so on, but this is the way to do the question in a slick way. And then there's actually maybe let's first take questions and then I'll say something more about this method. So if you have any questions about this method, please let me know right now. And then and by the way, just the final answer, it's just gm. Also, I don't know why I said little r squared, gm over r squared times sigma times pi r squared. So it's just pi gm sigma. That's the final answer. Somebody asked, this should also hold for electric charge cases. Shouldn't it? Absolutely. The math is exactly identical. So no reason it shouldn't. Also, my bad. I somehow implicitly assumed it was electric charges here because I was writing the force as pointing outward. That's my bad. It should always be pointing inward for gravitational. I guess got hardwired to the electric case and just made it pointing outward. Of course, it doesn't matter. It's just a negative sign. But yeah, it's so gravitational case is actually pointing inward. Okay, so just an alternative way to phrase this argument. This is just a weird way to phrase the argument, which some people like. I'm not a fan of it. I like the projection way to phrase it more, but here's another way to phrase the argument. So we make an analogy to the following setup. Imagine closing the hemisphere with now the base. So now you have like a closed region with a boundary. And now imagine filling it with a fluid, and suppose the fluid has pressure P. Now, then we know that the force on the hemisphere part should be exactly equal to the force on the base part. Because the net force due to the fluid on the thing should be 0, because it's not just having a fluid inside the thing is not going to have the thing accelerate. And the idea is then you take the fluid to have pressure equal to sigma g, because that's this looks like a pressure equation. And then you just argue that, okay, the pressure on the hemisphere part is equal to the pressure on the bottom part, and the pressure on the bottom part, the force due to the pressure, is just sigma g times pi r squared. I think this is more confusing just because you're involving this pressure thing unnecessarily, where the projection thing makes more sense to me. But that's just, you might see this argument phrased in terms of fluids and pressure, making an analogy to fluids and pressure. Yeah. Any other questions about this one? And if not, I think we're basically out of time today. Doesn't this imply that if a mass is inside a spherical shell, it will feel no force? No, it only applies in the case of the center. So I assume what you're referring to is the famous theorem, the shell theorem. But this argument very heavily depends on the fact that the point is at the center of the sphere. Just every part of this argument depends on that. It depends on the symmetry of the setup. But the fact that a point at the center of a spherical shell feels 0 force is extremely obvious by symmetry. So so I think what you're going for is this does not imply the famous shell theorem, because you lose symmetry there. So that is true for a deeper reason. This is just some symmetry stuff. So it doesn't imply the shell theorem, unfortunately. But the shell theorem actually has very nice proofs. Okay, I maybe this just inspires me. It's a similar idea. We can actually prove the shell theorem very easily using and similar geometric tricks. I'll just go over that real quick and then we'll end. So the idea for so what shell theorem says is that in the gravitational context, if you have a spherical shell of mass, again, let's say with sigma, so like a spherical version, and now you place a mass anywhere, not just at the center, but anywhere, then it feels 0 force. This is not obvious by symmetry anymore because it's not at the center anymore. But we can actually see this using a geometric argument. So the way you do it is you sort of make a bijection between points on the surface of the spheres by sort of projecting through this mass. This is not a very good example. Like that. And the idea is that if you now take a little patch of area here, A1, delta A1, this is R1 and this is R2. Then the patch of area here, it says delta A2. These are sort of like cones coming out of this point. What it tells us is that delta A1 over delta A2 is R1 squared over R2 squared. Because they're sort of cones with the same angle, the same solid angle. And that implies that if you think about it, that implies that the force on the mass due to the top one is sigma delta A1, ignoring it's G times the mass times M over R1 squared. And the force due to the other one is G sigma And actually then delta A1 over R1 squared is equal to delta A2 over R2 squared. So this implies is that if you now split now that these two little patches cancel out. So now you can split the sphere up into all these pairs of patches where you sort of take a patch and you project that patch through the point and you create a new patch. So basically what you can do is you can take a top hemisphere, split it up into patches, and then use this method to sort of create projected patches on the bottom hemisphere. And that way, this argument tells us that they'll all cancel out if you pair them up in this way. And there's no net force. So this is in similar spirit, very slick proof of the shell theorem, just using geometry. This proof can be found in Morin, I believe. So if you want more details, you can look it up in Morin. All right. So I think we'll end for today. Any final questions about anything before we end? Let me stop the recording.